Okay, so welcome to today's lecture in neural networks and deep learning. What we today want to do is, on the one hand, first, finish a bit what we started last time. Last time we talked about PDNNs and RNNs, and we ended with this challenge of having exploding gradients. And therefore there's one work which is somehow maybe the most default RNN which are currently used, that the long short term memory networks. And these ones we want to look in a first step today in detail. After we have done that, we will then have a look at self-attention. What is maybe the default state-of-the-art overall of sequence modeling? I guess you've all heard about transformers. So they're the main component. Instead of using an RNN, we will look in what are the challenges or why it might sometimes not be the best, and then introduce this idea of self-attention, going through how we can implement the self-attention. And that will be then the second part of today, and we'll maybe finish that on Thursday. But let's shortly recap on what was the challenge. We visualized this problem of gradient explosion on this example of sentiment analysis. So the idea was we want to use an RNN which reads in a text and then tells us whether this is positive or negative. And we therefore use this type of RNN where there is one difference to what we had before. And we should highlight a bit more the challenges of RNN. And the idea was that we're not really interested in the hidden states in between. We only want to know at the end, whether this is a positive or negative review. So it's a sequence classification. And in generally, a sequence classification task, you can model this way, that you're having an RNN layer, and then your aggregation layer, which we called it before, is mainly you just take the last one. Because in an RNN, you accumulate all the information, and then in your last hidden state here, you have information about everything. And based on that, you can then learn the output, whether it's a positive or negative review. What we then saw is that, of course, we only can decide whether it's positive or negative at the very end. However, the indications why things are important might be somewhere a lot earlier. So these are the most important things is somehow maybe amazing, so on, which should be give us indication that this is a positive review. So what we have to learn is to take these features in and take them in learning that they're important. But when we're now calculating the derivation to how important is the previous were amazing on our final input, we have to somehow calculate the derivation of our loss here to some hidden state very far to the back. So if the sequence has a length of something like 115, it might be that on the position 50, we have to calculate, we get the importance of that. Yes?
What is the case if we have sentence, this is not amazing? So we have still amazing, but with not that one?
Yeah, I mean, that is, of course, something which we have to learn, but that you can learn mainly that, you're aggregating your information here, and somehow in your aggregation, you should learn that if there is a not, then you should store that. And if you then read an amazing, that it's somehow inverting that. That you can learn in between there. Of course, it's not easy because it's also not, and so on. But with a lot of data, you should be able to learn that. But these are normally strongly next to each other. So there's not the problem of this gradient. That is a challenge in general, but it's possible to learn that with RNN because you accumulate all the information. So your hidden state is different whether you read it is amazing or it is not amazing. That should lead to a different hidden state. But it's, of course, something very important to learn in that. So if we now want to learn that this amazing is important, we have to somehow calculate then and learn, for example, the right embeddings. We have to calculate the loss with respect to age 50. And if we're doing that, what we mainly have to do is we will multiply a lot of times our weight matrix WH, which is between the hidden states, and then we saw that this is a problem, then if this is not exactly 1, it either leads to that the derivation gets very high or it's getting very low. So if it's 1.1, you're already at like 419. And if it's 0.9, you're at 0.001. Meaning, yeah, you have there the problem that your derivations will either explode or get very small, which of course will make learning very, very difficult. So the question is, can we do it a bit different? And this is somehow a major motivation for what is called the LSTM-based models. There's several ideas implemented in the long short-term memory. So the first thing is the problem is we saw that WH, if it's not exactly 1, we'll have the problem that it goes up and down, like either explodes or gets low. So we're trying to build a model which they then call the so-called constant error carousel, where we are having the WH is just 1 always by default. So we're not learning it, but we're just transporting always our information. And if this is 1, hopefully we at least have a less problem with the gradient exploding and the vanishing gradient. I mean, in the LSTM, this is also not, of course, completely solved, but it's like a major issue, and we want to do that. Furthermore, there are these conflicts that, for example, for the input weight, like into your network, on the one hand, you have the same words for whether we want to like store this information into the network or what information you want to store in your network and whether you want to use the information or not. It's not that we separate them. So should we store this information or not? And another way deciding, oh, if we should store it, what information should we store? We are merging these two things. Also for like getting information out of the network, it's the same thing. You're like having one weight which says which information should be out, but you're not separating them into one decision. Oh, should we use information from the hidden state and output them? And if we should, which information should? And all of this is somehow addressed in these in this type of LSTMs by having defining some sort of gates which do exactly this decision. So they decide, should we write or should we ignore it? And then you, in the second step, only decide which information you put in. And this is implemented by an additional memory cell. So currently we had our hidden state, which is transported over the time in there. In the LSTM, now you have an additional memory cell which should store some information. And there we have exactly this intuition that we try to commit some inputs. We're saying, oh, this information we want to store, and then we might want to store it for a long time. And later you can have a gate again to decide, should we now read from the cell or should we not read? And if we read, what information do we want to read? And also there's a third option then, oh, we want to remove information from it in order to do that. We'll later see, for example, I mean, one motivation where you can think about that is if you process text, you might want to know whether something is in quotations or not. And this is exactly what then one of these cells we'll see can learn. So somehow you're storing this cell only, are we currently within a quotation mark or are we outside? So meaning if you read a quotation mark, you're like storing there, now we are inside it. Then for a long time, you're doing nothing. When there's another quotation mark coming, you're reading, oh, no, I'm outside. So you're removing the contact, you're reading that. And so you can later access, and you have one parameter which only checks, are we currently in a quotation mark or not? So how can we implement that? And this is mainly done by, as I said, these 3 types of gates, the so-called forget gate, input gate, and write gate. And let's have a look at them one by one. So maybe the first 2 things is here, the 2 horizontal line you should see of. Now, as I said, we have 2 like somehow hidden things we have. We have our cell state C that stores information for a long time, that's C, and we have HT, our current hidden state that we read out. So the CT is like just for storing. We can't directly access it. We'll see how we can access it. But the HD is what we in the network also give to the front. So you have two things here. That is the first important thing. You have the cell state and the hidden state. And now you have gates defining whether you read or write something to your cell state. The first thing you're doing here is you're defining whether you want to forget something or not. So should I keep my cell state or should I remove information from the cell state? The question is, how should I decide whether I remove information from the cell or not? And this is based on two, and this is the case here for all gates. This is based on the one hand on our current input xt, as well as on your previous hidden state. So we're never using our cell state except for writing out. The control is all done via our hidden state. So we have our hidden state and our xt, and based on that, we are not doing the forget gate. Sorry, we're the output gate. This should be the forget gate. So the forget gate is defined this way. So first, we're doing as we do a normal like feed-forward neural network. So our decision what we should forget or not is based. We're taking our input. We're just multiplying it with a matrix. This is our matrix WFX, and we're taking our hidden state and also multiplying it with a matrix, and then we have some bias to it. So it's a normal neural network where you put in XD and HD, you concatenate it, and then you're predicting, should I forgot it or not? As an activation function, you take your sigma, so it's between 0 and 1, and then the idea is we're multiplying it later. You see already here with your cell state. And the idea is if your output is nearly 0, you will forget it. It will be deleted because you're multiplying your previous content with 0. If it's roughly 1, you're just keeping it. So that is achieved by the sigmoid activation function. So you mainly have here a small neural network, which only task is to model whether we should forget what we have stored before or whether we want to keep it. And that is decided based on not the cell state, but our current hidden state and the input. So if you read something, you first want to know whether you forget it or not. Remember again your quotation. What you have is, for example, if you read a quotation and you know you're currently not in a quotation, what you should do is, oh, then I have to delete. I'm no longer in a quotation mark. After forgetting, you want to put in new information into your cell state. And that is controlled. Again, we're not just, I mean, this is now again this idea, we're not always writing things in there, but we have an additional gate which first decides how much information should we write in. We're not doing it as discrete because we want to have calculate derivation. So it's a smooth function, so it's not the 0, 1, either we write or not. But we have like the sigmoid function with values between 0 and 1, which decide whether to write or not. The gate itself is exactly the same. So it's exactly as our forget gate. The input is based on the input gate is defined based on the current input and the current hidden state. You have again some of our feed-forward neural network based on that and the sigmoid content. And with this one, you decide now, should I write content to it or not? That's the one question. Once you have decided whether you write it or not, you have to decide which content do I want to store in there. And that you do with your candidate content. You see it's again the same type. So what you want to write depends on your current hidden state and on your input. And you're defining, again, a network based on that. So you have different weights here, W and W, which do this type of writing. And that is now your candidate content. So based on your input, you're first deciding, should I write or not? And then secondly, based on that, you're either writing or you're not writing. And that then combined with your cell state will give you your new, with your forget gate, will give you your new cell state. So the new cell state CT here is first, we take our forget gate and multiply it with the old content. So it's FT times CT minus 1. Forget gate is between 0 and 1. If you want to forget, it's 1. So it's 0, sorry. Then you multiply your old content with 0. So it's released. If you want to keep it, should be around 1. Then it's just your old cell state. Now the same thing happens with your input gate. So you're first defining what you want to write, or I mean, which way you're doing it in parallel, and you're defining whether you want to write or not. If IT is 1, then you want to write something, then you're just adding the new content to the old one. If you think, oh, I shouldn't write, then you don't do that, then IT should be around 0, and then you're not writing it to them. And so you have it visualized up here. So you have 3 things, 3 times here, mainly a network which predicts something, 1 gate, 2 gates in green, the forget gate, and the read gate. Then in purple, you have here what to write. You're combining that always with multiplications, the gates with what you want to gating. And then you're adding up your previous hidden cell state with the new content, and that's then the new cell state CT. So with this, we can now control what we want to store in our cell state. It's context dependent based on your previous hidden state, and it's based on the input. These are both influencing both whether we decide what to keep and when we decide what to write in there. So there we have now CT, and the next thing then we have to think about is what do we output? We're outputting mainly our hidden state. The hidden state is then put into the next higher layers typically, but before we are going into there, first, any questions about how you update your cell state? Yes?
Is there a difference between the star operator and the dot operator in the last line?
Sorry, no, that should be both two, that are both two vectors which always just get multiplied into a new vector. So it's like, I mean, it's not a scalar product, that's maybe this one is better. So it's really like first dimension by first dimension times first dimension, second by second. So then you in the end want to have again a vector here. So you take this vector and then multiply these 2 dimension by dimension. So this should be transposed and this should be transposed. So the multiplication is here the same.
Okay.
Yeah. Okay. And then for the output, we're doing it somehow similar. We are again not just deciding what we should output, but we are first defining whether we want to output something or not. And then we're outputting in it. So first, we have this output gate, which is again like a gate, and you see the formula is very, very similar. So again, we're defining whether to output or not. It's not based on the cell, it's all based on our hidden state and based on our input. So it's again, mainly a feed-forward network, which takes XT and HT plus 1, combines both, and then decides, should I output things or which information should I output or not? And then we're taking these, and that will be our new hidden state. So the new hidden state will be based just on what we read out from the cell state. So we take the cell state, make a nonlinearity around it, and then we're just multiplying it with our output gate, deciding which information we should put out. So in summary, that is our overall LSTM architecture. The important, one important thing is definitely the 3 gates. So we have the forget gate, deciding whether we want to forget something, the input gate, deciding whether we want to put something in there, and then we have the output gate to decide which information we put into the next hidden state. The important thing is then also, so the HT and the input, they are controlling everything. The cell state is only there to store information, but the cell state is not influencing whether we output something or not. Maybe also important, the HT, this does not directly depend on HT minus 1. So it only has content from CT. Only through the gating, of course, HT can control how it's, HT minus 1 controls which information are in HT. That means then, if we're doing the backpropagation, we're going like from HT to CT, and then you can go like here quite fast, because when you do here your formula, you not always have the same type of multiplication. The only multiplication you're doing on that is like based on your for get gate, and that is not in all positions the same. So it's not that you always multiply the same thing on to it, but sometimes you multiply different types of for get gate towards it. Any more questions to the type of LSTM architecture? I mean, this should especially, of course, also tell you or like give you an idea of this type of gating mechanisms, and they can be helpful for other situations also. So it's not only that gates are only used here, they might be also used in other types of networks. And if you want to like somehow control the flow of information, there's like this type of mathematical formulation gives you the option to like control that by the content and not process information always the same thing. Then some more like general ideas of how they or how we can train things. So if we are training, then now we can train for very long sequences, and I mean they're influencing. However, there is somehow more than a computational problem because you have to store all the sequences. For text, that's partly possible, but if you're going now to audio or video frames, sequences might get really, really long. And then things get significantly complicated. So therefore, in training of these RNNs, what you partly do is a so-called truncated backpropagation, that you do the forward pass normally, but the backwards is only like truncated at some positions. So you're not modeling the influence here then anymore. Only the activation is modeled. So the forward pass is done completely, but the backward pass is truncated at some. Of course, you can't learn then dependencies between these long things directly, as that's why you need some outputs in between, but it's just like computational no longer possible to do really both things, and that's why people try to address it in this way. Then some more about the computation before we are looking at this type of visualization. So what we have now is like, just to do a bit of step back, we have now a good representation or like good implementation of an RNN. We talked also about CNN and TDNNs. So what is the similarity again if we see these both as like sequence modeling things? So we see that the implementation or like the training is not completely really different. We always have this idea that we roll out the network over the sequence length, and then we are sharing weights, and we have to like share weights and make sure that the weights don't change. We can increase in TDNs the contents by D. So by the kernel size, we can have longer context, but we always have like somehow a fixed predefined context size. Also, if we increase D, it means we're increasing the number of parameters. So that we should keep in mind that this is always somehow the problem, that if you want to have larger context, you need a larger kernel size and more parameters. Therefore, you have the nice thing that this type of gradient, vanishing gradient is not, or exploding problem is not really there. For RNNs, in contrast, we can have flexible adaptive variable lengths, but you have this problem of gradient vanishing and exploding. It's not in LSTMs as big anymore, but still you repeat similar operations over and over again, and it's still somehow challenging. One other important thing is about the computational cost, and that we will especially address in self-attention. In the CNN case, the hidden state at one position is not depending on the other hidden state. It's only depending on the input. So you can process a whole sequence in parallel. You can in parallel calculate the processing in parallel. While if you think about an RNN, your new hidden state in LSTMs in all of them depends on your previous hidden state. So you have to do this sequential processing. So always process the current one based on the previous one, which then always will lead to the problem that computation might be long if you have very long sequences. So it's depending on O of t. Good. Before we are finally looking a bit on the visualization, any more questions? Good. Yes, this is the last part, and we want to look a bit. I mean, it's very difficult always to like inspect what the networks really learn, but there is some work on like trying to get a bit an idea of what these networks really learn. And what this work does, it looks at like the tangent CT, so your current CT. And if you have CT like your cell state, it's also a multi-dimensional vector. So each of the HD and CT is like has the same dimension normally, and it's like having you have a vector there. And now you can look at each entry there and try to inspect it, like what is somehow stored there. And to be honest, most of the things it's not easy to interpret because like there's complex combination between the different dimensions, and it's not clear like you cannot interpret each of these dimensions individually. So one example is here. So you have here a code snippet where you see whether the value is high in blue or low in red. So since it's tangents cobolicus, it has always to be between 0, 1, and 1. So you can look at least the authors of the paper and me also. I don't see there like a clear pattern, like what in this one vector there has been stored. So that is not like straightforward possible. However, which is maybe interesting, you can look at some of them, and I mean you can look at all of them. So think about you have a hidden size of like maybe 500, so you can now go through them and visualize it and see whether you find something. And the interesting thing for some, you'll see things are happening. So one thing is there seems to be a counter of how long the sequence is. You're seeing here, it starts with very low values in blue, and then getting no, it was other way around. Yeah, red. So it starts with a high value, and then it's decreasing at the end. It's knowing, okay, we are done at the end of the sequence. So it's somehow doing this type of counting, like what information are still there or what is missing to have a full sentence. You can think of that, of course, important. If you want to language processing, you need to know, is this a complete sentence or not? And this is a bit like what this one cell does. There's the other cell here, which does information about whether this is a quote or not. And you see very nicely, so yeah, once the quote starts here, so here starts a quote directly at the beginning, then it's blue, it's high, then here it ends, here it's red, and there a new quote starts and it's blue again. So there is one thing which does that, and you can again think about if you want to do language processing, might be important. How text is formulated within quotation might be very different than outside, so it might be a very important information. You can train these, of course, not only on text, you can train them also on code, and then you also see interesting things, like, for example, here you have one which seems to look at the condition of an if statement. So always if there's an if in the bracket, everything mainly within the bracket is highlighted. So it's like focusing on like what is the condition to go into this. Or you have another one which is highlighting somehow the comments within code. Also differentiating, there seems to be a significant difference between things that are within the comments and things that are outside of the comments. Good. So this was now like in 2 hours, 1.5 last time and half an hour this time. More detailed look into how CNNs, TDNs on the one end and RNNs are working. They are both like there for representing sequences. The one is like always having a fixed size context window. The other is storing things over time, where we then saw the problem of gradient exploding. And we saw then how one way of addressing that is like using LSTM-based models to better learn them. Do you have any questions to these types of models? Good. Then we will switch to the next presentation. Sorry. And what we will do now is, I mean, RNNs are were like the first one to really represent well on sequences. If you think about text and audio processing, somehow it was like the first thing where people successfully did that. What we see now is that, however, there is this problem of one is a vanishing gradient. We're also seeing you have to store everything in this type, like one fixed vector, which makes things difficult. And then one last thing maybe, which is not to underestimate, is the problem about the processing. So we say we have to process everything one by one and can't do it in parallel. And that all these challenges gave then rise to a self-attention, which by now is somehow the default thing. I mean, if you think about all currently like existing large language models are mainly based on the idea of self-attention. Therefore, we'll look into this now in more detail. What we want to do there is we'll start with the motivation why people looked into self-attention. And then especially what the idea of self-attention is that we are always creating individual summaries at each time step, which summarize all our information into a new one. And we'll look into like how we could do that. And then we'll first having more detailed look at the attention. We will describe the idea and then the exact calculation, how you can calculate a self-attention layer. Then there is different extensions to that. There's a cross attention as well as a multi-head attention. And then in the third part of the lecture, we'll see that one problem is about how you encode position. And position, of course, is essential. If you want to do sequences, it's important to know where these information are, and they have different meaning. This is attention a bit handled a bit differently than in RNNs, and that's what we want to look at different like positional versions, like positional encodings, and how to do that. And finally, even though this is motivated, of course, that we can do, I mean, the idea of this was really somehow a co-design between a network architecture, which already fits well with GPUs where nowadays all the calculation is done. There's still, of course, not everything is perfect. And then if you now want to build like large models, which can take long sequences, the default thing you will see is what is called flash attention to make more efficient calculation. And that we will look then somehow more to the end. Okay, with that, let's start about why should we do another sequence model? We have already a sequence model, and in general, we have this idea we want to learn a sequence representation. And now we can do now, you have now the knowledge to do that with a CNN or with an RNN, and especially with an RNN. And with an RNN, you're doing that with this idea. You saw that you process and you use some of the same network at each position, also with the CNN. In order to have the parameters, you're doing that. In an RNN, we have the big advantage of having global context. We just learned that before. Again, repeated, that's a big difference between the CNN and the RNN. We have global information. Again, if you think about this example with a sentiment analysis, you need to somehow store all the information during that in order to answer that. If you want to have something which processes a whole image or like a whole long text, it might be that you're referring to something in there, and there you need to have information about everything. So you have to store some of your history. However, in an RNN, what is important is we are storing the history in our blue thing. What is the blue here? Oh, I wrote it. It's a vector. So this is always a vector. So here's a vector, and here's a vector. And the vector, important thing is an r to the power of n vector, meaning it has a fixed size dimension. So we can't store like just anything. We have a fixed size representation, and we have to deal with this fixed size representation. We cannot like extend it to like sometimes store more or store less or things like that. So you have to keep in mind, yes, we have a bit like a contradiction there. We want to store global information. We want to store information of variable length size. So you have very long sequences where you don't know the size. But at each time, we have to store all these very long different information into like a very fixed size representation. And of course, it's not clear somehow what you always should store. It's like, I mean, you maybe if you want to do question answering, you might want to answer question to the beginning or the end, and it should always work. So you don't know, should I store information from the start or the beginning, and which information should I store? And so you have this type of challenge that you store this in a fixed size, and things can happen that you start to overwrite things. I mean, if you get new information, you need to store them at some point. Just your fixed size representation is fixed, so you cannot easily extend more. If you think about it, your hidden size is a bit like as your paper. You're going through the lecture, you're doing your own notes, and you only have one paper. So you start at the beginning of the lecture, you write down what you think is important, you continue, and your paper gets full and full. At the end, at some point, you've just written the full paper, and then the question is, what should you do? And what an RNN does, it doesn't have more. So it thinks about what information might no longer be important and overwrite them and so on. So it's you might lose information, and that is, of course, in some way difficult. And the question is, can we build an architecture where we don't have this problem, that we are not knowing really in this position which information from which steps before are important. So when we're at movie, we don't know which information before there were important, or no, other way around. If we're here, we're not knowing that which information there will be important. So it's really difficult to store in there. So if you now need to write down your notes, you don't know what you'll get asked in your exam. In your exam, you maybe know then later, and would be maybe nice to like look back and check what you have, where the answer was. But you have to store everything during the lecture in your brain and be best prepared. But there's also like limited time and so on to learn. Then we saw there is these long-range dependency. We have addressed them a bit, but still all RNNs, even LSTMs, often have problems to learn really long-range dependencies. So that's still an open question. We'll see even with self-attention. But if you now want to learn things like planning, where you have have decisions and you want to find the shortest path or so, these are typically very difficult for these sequence models because like your decisions very at the beginning might influence very late decisions, and that's just very hard to learn. And finally, you have the problem that your computation depends on the computation length. That's what we know. So you cannot just calculate all your hidden states in parallel. What you have to do is you're somehow do it one by one and only know at the last, when you can only calculate the last step when you have calculated all previous steps. So you cannot do everything in parallel. And I hope you remember a bit, it's some weeks ago, but we had this type of GPU lecture where we are motivating, for GPUs, it's very good if you can do things in parallel and a lot of things in parallel. This is somehow exactly not doing that right. You have to do it sequentially. You have to do one hidden state at a time. Of course, at each hidden state, you have some parallel computation, you have all matrix multiplication, but you still have to do it like one by one and cannot do it all the time together. So the question is, can we do things somehow better or different? And yes, we can, and that is the main idea now. Can we somehow focus on different parts every time we process? So when we're doing the last word, we don't want to store like everything in a fixed vector, but when you process much, you want to somehow look back and see and look, oh, which parts of your sequence was important, and then take these ones and do the computation. So you're not always doing, you're not for each hidden state store everything, but in contrast, at the end, you're deciding which informations now might be important, and then look back and check the individual. So again, a bit like more an open book exam, you're in the exam, you know, this is now the question. Now you look back into your slides and check which answer you have. You don't have to store everything when processing the lectures, but at the end, when you have to do something, you have access to everything you had read before, and you can access that and get your information from there. And you can always focus on different parts. So there we'll see the main idea of this self-attention, that you put attention or focus on different parts. So you're focusing always somewhere different. How can you do that? I mean, you want to focus, you want to do somehow summarize the whole sequence into one hidden state. The first idea of summarizing, or the easiest thing if you think about vectors, is to do like a sum of the states and choose them. Just this type of sum has, of course, one somehow disadvantage. What is a bit of challenge of a summing operation?
Doesn't consider the order of the sentence or the words in the sentence.
The order, yes, that is true, but we're even not for the advantage. The order will come later too, but it even has something. If you think about focusing on different parts, it's not only the order it doesn't consider. Yes?
It does not consider importance of some words.
Yes, exactly. So this is also correct. It's just like currently our first will address that. So this is like the sum will always be the same. If you're summing a sequence, it will be always the same. You cannot say, oh, in order to understand my last word, maybe this time the second word is more important. I want to look at all, but not all are equally important. And not to understand one, like if you have two different words in this sequence, you might want to look at different parts. If you sum, you'll always get the same result. However, there's a very easy extension to the sum so that you can focus on different parts. What you can just do is you do a weighted sum. So instead of taking the direct sum, each of your inputs, 1, 2, 3, 4, you can somehow weight them and say, oh, how important they are for my current understanding. Then you can still look at the whole sequence. You have a variable size input here. You're summarizing them into one hidden state. But this time, it's not always the same. Depending on the weights, you might focus on different things. And that's what we want to do again. And that's mainly the idea of self-attention, is that we can do it like we're not just building a normal sum, but we're always doing a weighted sum based on what is currently information. And you'll again see there like something similar to what we had before with the gating, that we put somehow importance on which information we want to use. But before we're going to the details, let's have a look and see how we can build summaries and how we can summarize somehow our vectors that we have. So when we now think about a sequence, you remember at each time step we have a fixed size vector, and we want to somehow summarize these vectors into a new one. How can you make these types of summaries? And therefore, how this is done is like strongly correlated or like inspired by retrieving from databases. And just I think for you it will be important to remember this correlation, this idea from databases, because a lot of the terminology we'll see is like not several directly maybe clear, but if you always take the similarity to database, I think things get easier, because we also will talk about query keys and values, and you might get a bit like confused. What is a query? What is a value? And so on. If you there remember this type of database idea you have, then at least I assume it's easier a bit to understand these things. So how is it now correlated to so imagine, in order to understand your last word, you're taking all the words before in your sequence, or all the items before as a database, and what you're now doing is you're taking your current position as your query and asking your database what information are important from the previous sequence in order to understand this. So how does it work in a normal database? Just imagine you have this price index, like from a restaurant, cheeseburger, fries, hamburger, and ice cream, and you have values, maybe the price, and now you want to know how expensive a burger is. In a normal database, what you're doing is, so first you have your query, which is burger, and now you're comparing your query to your keys in order to find the key which you're searching for. In this case, this might be hamburger. And you see already one thing we'll not do exact matches. I mean, if you think about neural networks, it's continuous values. So when we query and compare query and key, we are looking not it is the same or not as in databases, but you have more this continuous one where you calculate a similarity, saying how similar is your query to the key, and higher values indicate somehow this is more similar and lower values this is lower. And then you could take the one which is most similar, which could be here, for example, hamburger. And then you would take the value 10 and return, okay, 10 is the current price. In attention, we're extending this a bit, this idea of continuous thing. So what we're doing is we're comparing our query and our key and then calculating similarities. So within the query, we are comparing it to all the keys. And then we're getting here similarity. And we could, for example, assume now, in this case, sorry, here. We have, here's a similarity of 0.5, and here's a similarity of 0.5. So that is important. Now that's a bit going away or extending the normal database where we're not having exact matches, but more similarity. And then our return value, when we're returning, is also not exactly the value that we have stored here, but we have stored with every key a value. And now, like if we don't know, is it cheeseburger or hamburger, I guess the typical thing you would answer is maybe it's somewhere between 10 and 12, and you have to answer with one number, you might take the average. And that's exactly what you're doing. So you're doing the weighted sum by multiplying your similarity. So the similarity is the similarity between the key and the query. You're multiplying this one with your value, then you're doing a weighted sum, and then you have 11. So then you could say, yeah, 11 seems to be a decent answers to how expensive a burger is. So there are two types of burgers. The one is 10, the other 12. So this is like somehow a good summary. And that's how we will implement it also in the neural network. So we're using some of our queries, comparing them to the key, calculate the similarity. The similarity is then multiplied with our values to get one final thing. And again, we have here a database which can have unrestricted number of entries. That is our sequence length. We have here a fixed size representation in, and we get a fixed size representation. And now we get a different summary based on what we ask. If we ask about burger, we get the price of burger. We ask about hamburger, we will hopefully only get hamburger as 1 and the other is 0. You get 10. If you ask about ice cream, you get ice cream. So in order to understand things, you will always get different summaries based on your input. And that is also the idea of self-attention. Based on your query, you're always looking which information from my database is important, and only return then a summary based on this importance. Okay, now we did it maybe very far away, more to explain what query key and values are. Now let's do the step back and look exactly on our network how that works. We'll first do it a bit on a higher level, and then we will repeat each step in order to look at how that now works when we're like how all the math behind it works step by step. So we're mainly doing it twice, but I think it's very important, so it's good to understand. So again, we're having the important two strings, the query, the key, and the value. And hopefully now you have a bit of an intuition what the query, key, and value is, because it's behaving exactly as we have it in the database. So we're starting with our sequence. 1, 2, 3, 4 is our sequence. Important thing you will see, it doesn't matter how long your sequence is, your calculations somehow works on. What we then do is we're taking we want to calculate now our new hidden state for the first position. We're now later looking what is important for the second and so on. But first we want to look what is important for our first position. Then we are using the first position as our query. So in yellow here we have the query. So we are using this one as our query. Then for each position, we also have the keys. So the sequence is also the keys that we're having. You already get the idea of self-attention. The self is we're attending to ourselves. So the sequence is looking at itself in order to understand what is important. But the first word is looking now to all the other words. And what we're doing is we're comparing our query of the first word with the keys of all, and for each key, we'll get a similarity value, saying how important is this position in order to understand this one. And there will be our orange values here, which are just weights. So they're scalars. They're not vectors anymore. This is just a scalar telling us how important these positions are. So most probably, often one will be very important because to understand the first word, you need to know the first word. And then other words might also be important that then depends on that. What you then normally also do, that's more a computational thing. These orange ones, you're now normalizing to make it a probability distribution using the softmax. So meaning that these values here will be all between 0 and 1, and the sum will be 1. But this is more a reason for stability, again, that you're not having very huge or very small values that you can't process them anymore. Now you do the second step from what we had before. Now you have to calculate the new hidden state. What you do is you're now taking here your values, you're multiplying with the orange ones we had, the weights. So you have then a weighted sum, and then you're summing them all up, and that's your new hidden state. So you're based on your inputs, you're calculating the values. The values get multiplied with your weights you calculated before, so on what you put attention, so on which parts you should look at, and then you have your weighted sum, and that's your hidden state. What you now have is you have calculated based on your input sequence one new hidden state. What you of course want in the end is, I mean, we saw that in RNN and CNN, what you get is for each input, we get a new hidden state. So we want to have this, what we call one-to-one mapping between the input and the output signal. So the next question is that now we have one hidden state. How can you calculate now the next hidden state? Any idea? What do you need to change to get now? I mean, you can also ask it differently. Why is this hidden state associated to the first and not to the second, the third, and so on? Yes?
But we use the first word as the query.
Exactly. So this is like associated to the first, because the first one was used as query. The query defines then or leads to different importance here to where to focus. And that's why your weighted sum represents a bit what is important for the first word. That, of course, now makes it very easy to extend it to the second. What we just do is, we're just using the query, the different query. We're now using the second word as our query, and then doing the same calculation again. The only difference is now, of course, our orange values will be different, because now we are not getting this by comparing the query of the first word to all the keys. The keys are still the same. The difference is the query is now from the second word. So also, therefore, the comparison will be different. This will be most probably very important, and maybe other words will be important. And then we're normalizing them again. And we're doing the same thing. The values are the same. This value is only different because due to the different query, the importance here is different. So we get a different weighted sum. So somehow at each position, you do a weighted sum. But the difference is that your weights are different. So the elements you sum over is the same, only the weights are different, and the weights are based on your query, because you're always asking which is important, which part of the sentence is important in order to understand my current position. Good. Did you get a first idea of how this could work? Or you have questions first? Yes?
What is the difference between the key and the value there? We kind of compute the value from the key in that case, but how does it differ?
You just do a different type of transformation from that. And the idea is maybe other things of your input is important to decide whether you want to use it for comparison, to decide for which elements this is important, compared to what information you want then to put in. So there's two ways of maybe motivating them. The one thing is, again, you can look at your database. So there's the key tells you how you should compare it to your query. So whether this is the same or not. The value is then which information you want to give away, so the price. You can also compare it a bit to the gating. You once decide, are these information important for the other tokens? So the key is somehow related to the gate. And then the value is which content do you, in this case, want to give away? And this question is very good in a way that we'll see later. I mean, before attention, there was cross attention. We'll come to that later. But this difference wasn't made. So it's not that you have to make it. It just like somehow it works better to separate these two ideas. You can, of course, merge them again. Then you might have the problem that you have to somehow learn, and it might not be as good. But I mean, generally, it's completely right. You can do that in one component. The idea is to separate it in order to have a separate decision whether you want to use the information, and if you want, which information then you want to use. Any more questions? Good. Okay, with that, then let's go a bit more detailed and try to have it and look at that like one by one. So in self-attention, what we have is, again, of course, our input sequence. So X is our input sequence. And by now, hopefully, you know the input sequence is a sequence of length n, big N, and each entry has then like a size of small n. So you have each element in your input here. The green one will be a vector of size n, and this is our input sequence. This is the case for all type of sequence models and also self-attention. And the first thing you're doing in self-attention is to calculate these three things we have that are the query, the key, and the value. And you need the query and the key and the value for each position. So at position 4, we need a query, we need a key, and we need a value. We need the key in order to say how important this is for other positions, the value, which information to transport to the other position, and the query in order to calculate also later a new representation for this one. So you need all the three things in there. And you're doing that by just a normal like feed-forward network in some way. You're just doing W times WQ, WK, and WV. So you're just doing different matrices for all of them. And you're always multiplying them with XI, with your current hidden state. And that will give you, we'll refer to query, key, and value as Q, K, and I. And the matrices are like that as a joint matrix of all the Qs, all the Ks, and all the Vs. Now you also see nicely, I mean, you can, of course, do key and value, some are the same by just having WK and WV exactly the same type of what maybe is, or no, what is important is these are all the parameters you can learn. So everything you can learn is based on how you represent the query, how you represent the key, and how you represent the value. Afterwards, we now do all the computation to calculate our final hidden state, but there are no parameters that you can learn anymore. So if you want to learn which information are important in order to understand the second position, this has to be encoded into your weight matrix WK, WQ, and WV. Somehow when you have defined then everything is fixed and there's just more calculation. So you later need to backpropagate always to this position in order then to change your matrices W, Q, K, and V in order to decide what information are important and which are not. So these are some of all the parameters you learn. Later there's more calculation on doing it, but this is everything you can learn at the beginning. Good. First, any questions? So now we have not really done anything about self-attention. What you again see, the learning thing is what you put into this type of calculation. That is where you have your parameters Q, V, and K. Now we can do the individual step. So the first thing is we said we have to calculate our similarity. So we have to now calculate how similar is the query to all the keys. In total, you have to do the all-to-all combination. So we are now visualizing that only to calculate the first hidden state, because it's getting complicated showing that for all. But you iterate that now over all possible values of Q here. So you'll see at the end, you have this matrix where you compared every Q to every K. You have the full matrix of like all importance. And of course, it doesn't need to be the same. It can be that word 4 is important to understand word 1, but word 1 might not be important to understand word 4. And that is represented that the queries and the keys are different, and you can learn which one is there important. So what this is represented is some type of active energy function based on your key and your query. So let's say Aij is the activation based on query E and key J. And now there's different ways of how you can calculate our similarity function. So how decide how similar Q and V are? Does anybody have so you have mainly now two vectors, and you have to decide, do they match to each other? Are they good or not? How would you define that? Yes?
You could use the scalar product.
Exactly. And that is somehow even though the one which is most commonly used. So what you're really doing is you're just multiplying your query matrix with your key matrix, and then you're getting there the activation. So it's a scale dot product, query times key. So you can even do that. They're all in parallel. If you have all the queries and all the keys, you're multiplying them across the key dimension, and then you get a new dimension of length sequence, which tells you each element in the sequence, how important that is. So you're taking your key, you're multiplying it with all the keys in the, you're taking your query, multiplying it with all your keys in the matrix, and then getting a sequence of all the similarities. Typically, you're doing here some normalization. That is because if the dimension of your query and keys get very high, then you have more variation, which makes things difficult. So in order to keep things stable in training, you're normalizing it by your key dimension. Based on that, in this case, if you use this type of similarity, does it like say anything about our query and key vector, how they have to look like? So here we had, okay, yeah, we have defined it this way. But in generally, query and key, the dimension don't need to be the same. But of course, if you do a scalar product, they do have to be the same. So you cannot take like the query to be like 5-dimensional and the key to be 4-dimensional, then you can't build a scalar product. So in this case, key and query have to have exactly the same type of dimension to do that. In my slide before, I was a bit too, so this, as I said, is a default. That's why the claim that these are the only learnable parameters is only, to be honest, true for this default thing that you do this type of comparison. Especially in earlier works, there were some works on doing the similarity, which takes additional parameters. So where you can learn a bit this type of a similarity function, and you have parameters. The idea is then, okay, maybe you have less parameters at the beginning to calculate your query key and value. Instead, you have more parameters in here to learn the similarity. So another way of doing that is that you have an additional weight, weight matrix W, which multiplies, which mainly learns how should I compare query and keys. If I'm completely free in my query and keys, of course, I can somehow learn that already in my representation. But it might be more helpful if I'm in some way restricted, or if the dimensions out of some dimension, you can also have like a multiplicative constant here. In the first work on attention, so not self-attention, but general attention, even they used a whole network in that. So the idea is to do it differently. Instead of building your scalar product, what you can also do is have a small network, which takes your query and your key as input, and then returns a scalar, which says how good do they match together. These are, of course, more powerful than just doing the scalar product. Does anybody have an idea why still people no longer use this type, but just use the type of scalar product? Any idea? What could be an advantage of just using the more simple idea? Typically, one thing which simple things are have an advantage compared to complex things. Yes?
It's faster.
I think you want to say them. Yes, so it's faster. It's like the right type of. Sorry, yeah. So you can do fast calculation that's faster, and you don't need, if you're doing this type of learned mapping before into query key and value, you can have most of the calculation here already, and you don't need that much powerful, because you can learn a powerful representation where just the normal scalar product is then already a very good type of representation. And that's why currently that is typically done, that you just take the scale dot product in order to do that. Okay, so then we have calculated our activations here. What we then will do is normally we're normalizing that. And that is again to prevent vanishing or exploding gradients. Just imagine you have somehow now a representation where this query is very different from all the others. Then your scalar dot product will be very low here. You'll have only very low values, which also will make your gradient then very low because you're just mainly putting zeros out there. So that is, of course, not what you want to have. And we can easily do that. We have learned the softmax activation function. So what you can do now here is you do a softmax over the sequence. For the softmax, there's no parameters, so it's no problem to do it over variable lengths. Doesn't matter whether you have 4, 5, 6, or 7 values. You can just calculate the softmax by like normalizing everything by its length, and you'll get that again, and yeah, that will give you the right value there. And with that, you're already at your last step. Now you know how important each element is. That is like how important the element is. You see here, like in orange. What you now do is at each position, you're multiplying this value with the importance with your value. And then you're getting these values. And the only thing then you're doing is to sum them up to get finally the one blue value here. So you're doing the attention, you're taking then A times the alignment we had before, times the values. So you have here, this is length sequence. These are just scalars. You're multiplying them with your values, which is a sequence times value dimension. And then you're getting one vector, which is again value dimension. So that is your new hidden state here. So in summary, you have like 4 different steps. So first, you're calculating your query values, query key and values. Second step, you're calculating your similarity. Third step, you're normalizing your similarities to be a probability distribution. And finally, you do the weighted sum. So in total, you have here everything. So you do query times keys, normalize that, and do softmax around it. The resulting values you multiply by V, and that is then your new value, which you have here. So as input, you give a query key and the sequence, and as output, you get your return value then. And then you do now at each position, and then you have a new hidden state at each position there. Good. Any more questions to how to calculate the self-attention? As I said, this is by now some of the default things. If you do like see any type of sequence processing, you also see even for like other dimensional, like 2-dimensional visions, you won't be able to do that. And it's like the real, like the 2 important benefits you should keep in mind is on the one end, you can do all this calculation in parallel. So you can in parallel calculate all the hidden state. The blue one only depends on 1, 2, 3, and 4. It doesn't depend on the other blue values here, which will come to the right. So you can calculate the whole layer in parallel. You even only have to calculate once Q value, query value, key and value, and then you can do this here in parallel for all positions and so on. So you don't have to like an RN push things in parallel. It's somehow directly designed in a way that it's very good parallelizable with GPUs, and that's why people then could use a lot higher, larger networks. Typically, you don't do one self-attention. You do a lot of layers over each other to do that. The second advantage is at each position, you see now, we have information about the whole sequence. It's not like an RNN where you start to like accumulate information one by one, and only at the last position, you have read everything and you understand everything. Here, the blue one is influenced by all the inputs, and each blue one is influenced by all the blue positions. So information can directly, very fast, go across the whole network and influence that. The nice thing is, if the information goes fast, if you go in the backward path, your back propagation, information can also go fast from each position. So you can a lot easier learn which informations are important to what. So there is not that you process things by a sequence, but all information at once go to all other positions. Yes?
How do you parallelize the back propagation? Or do you use the keys and values if you have it once for all?
What do you mean for all?
Don't you have to update them?
Yeah, I mean, that is, I mean, so that's a very good point. So of course, you can do one in parallel. You cannot do sequences between the updates. So that is still on a higher level. So you cannot process like 5 sequences and in between do an update. But first of all, that's maybe another advantage of that is typically you have to use quite long batch sizes so you have to like know or average over a lot. But the parallelization, therefore, thanks for the question, is here more within a sequence. So in order to calculate one sequence, we don't have to wait for other parts. That's in an RNN, it's also possible. You can, like if you have 5 sequences, you can process them in parallel. They don't depend. But here you can even process like the same sequence altogether and don't have to wait for the previous one, which of course is especially important if you now think about long sequences. You typically can then only store one sequence in your GPU, and then you want to process the whole sequence in parallel and not do like step by step and doing that. Okay, now I think from understanding in the right direction, from how it was developed, this is the inverse direction. So first there was cross-attention, then there was self-attention, but the cross-attention is still also important. And the idea here is maybe if we want to understand something, we might want to have 2 sequences, and like the one sequence is then asking the other sequence in order to understand them. It's just a different type of application of attention, which is not for what we had before to learn a new representation for the sequence, but it can also, the same technique can be also used to influence one sequence by another one. That is then what is called as cross-attention. So you can imagine that there's, for example, the so-called encoder-decoder models. We come to that. Imagine you want to do one sequence and generate a different one. So a typical use case here is machine translation. So you have here your source sentence, and now you want to generate your target sequence, and you're not doing it with the same model, but you have one model to somehow represent your input sequence, and another model to represent your output sequence. You can also, it's also used if you want to do something like image to text. So you're somehow here representing your image, and now you want to generate a subtitle of this text. What you then need is called cross-attention, where you say, oh, in order to understand now, to know what I should do here at the first position, I don't want to ask the other things in the text, but if I want to describe the image, I now have to look at the image, look what information are there in the image, and then process it. And the only difference is now that your one sequence uses keys and values, and the queries, they can also come for another sequence. So what I mainly can do is I can now take my sequence A, B here, calculate a query out of that, take this query, compare it to all the keys. So in our formulation, there's no restriction that the keys and the values have to be from the same sequence. We're taking the one query, comparing it to all the keys here, calculating a similarity. We're mainly looking, if you think about this as parts of your image, what information of the image are now important to start my description. Then you're multiplying the value of this part with your importance, getting a vector, and then you're getting here a new hidden vector, which is somehow like now you're looking at, okay, with a query, I decide which information about the image are important, and you're getting one fixed vector back to describe the current one. Again, you have this advantage compared to other things, that you're not always getting the same value back. Like a database, you can always ask the image again, if I'm now in this situation, which information are now important in order to understand the text? So you can do this type of cross-attention where your queries are now from a different sequence. And the queries will always ask different information about them. Again, we have the big advantage that we are not having to think about one fixed representation, which encodes all information which are important here. But at each time step, we're doing a new calculation, which types are there important, and only retrieve these types of information. So yeah, what you're doing is the model, the query is the model that searches, the key values are somehow your data storage. And so one thing important is, of course, the keys and values, they have to have the same length, because you need one weight for exactly each value. You generate for every key, you get one weight. So keys and values need to be from the same sequence. And the queries, there's like you have individual queries, and you can have the number of queries is independent from the number of keys and values. That's why you can use one sequence to do your queries and another sequence to do your query. And I think now it's also getting a bit more clearer why it's called self-attention, because there you query yourself. So you ask yourself, what is in my sequence is important. In cross-attention, you're going across another sequence, and you're the one sequence asks the other one what is important about you. In all of the cases, there is this idea that I'm not like having one representation which always summarizes everything as an RNN, but in each time step we have a data, but we have stored everything in a database. Every time we do a query, asking which information are now important and returning them. Good. Any more questions in order to get it? So there's two like applications of attention typically. There's the self-attention and the cross-attention. The big difference is whether the queries are from the same sequence as the values and keys. While self-attention, they're from the same. So you try to understand what is other parts of the sequence are important. In the other thing, we are asking which other information from another sequence are important in order to understand. There is no questions about that. Then we can have a look at the next extension to that, the final one, which is I think implemented in mainly every current self-attention or transformer-based models, and that is called the multi-head attention. And the idea is now with a query, you have this opportunity to focus on different parts. So each time you query, you can like focus on different parts. But maybe even to understand a single word, it might be helpful to not do one query and one weighted sum and say, oh, these words are important to understand them. But it might be, in order to understand some aspects of the last one, this is important, and to understand another aspect, other things are important. So meaning it might be better to not like once do a weighted sum and say these are important to understand it. You do it several times even for each position. So you're saying, oh, in order to understand my thing, I have to on the one hand look at that, and another thing look at that. So if you have the sentence, I like the movie very much, in order to understand what is in this sentence, the meaning of match, it might be on the one hand important to know that, yeah, you have very before, So vary is somehow important in order to see that this is like stronger. So you want to, on the one hand, take vary and much together. You want to tend to vary, combine these two to have, we have a strong emphasis on that. And the other end, of course, like is also important because this very much says that you like things very much. In order to what you want to make stronger, you also have to tend to like. And maybe you don't want to do that together, but it would be nicer to have like two ways of looking at ones that vary and ones that like. Again, you try to, if you want to understand something, there's two things which are important. It might be better instead of taking the average, you just look twice. You first look at the one aspect which is important, and then you look at the other aspect which is important. And that is somehow the idea of multi-head attention. Again, the idea is you have this head is like representing on what you're looking at. So what are you focusing on? Where is your attention? In multi-head now, you cannot only like put one weighted sum over it, but you put several heads, so several people look at different things. Maybe then again, you can think about it. You have the big crowd, and you're looking at it and want to identify something. Maybe it's helpful if not you're only looking, but you have 5 people who are looking, and they concentrate on different parts in order to better understand things. So how can you implement it? The nice thing is we can do the implementation with exactly the same number of parameters, just a bit of different computation. What we're doing is we have our query and piece values here, and they are like just n-dimensional vectors. We can now internally think of these n-dimensional or d-dimensional vectors as 2 vectors. The first half is the one vector, and the second half is the other vector. So you now, instead of interpreting your Q value as one hidden state, you're modeling as 2 hidden states, one of dimension d half and the other one also of dimension d half. And then you're doing your attention calculation first only with your lower entries. So you're calculating your query key and values. You do the comparison between query keys, get similarity values, then you do your you multiply your similarity with the values, you do the weighted sum, and you get your blue value up there. So that is then your first part of the hidden state here. Then in the second step, you do exactly the same thing as before, but this time with the upper half. So you again take the query and key, compare them, do the calculation, and so on, do the weighted sum, and you get your value up there. So you're doing it first with your lower part, then with your upper part. And finally, then you're merging them. So finally, you will then merge these 2 blue values, well, meaning that in the end, you have exactly again 1 vector. So now this is again d size. So your input is the same. Now you also have the audio again. Okay, so I don't know for the ones who are recording, I'm not sure, but yeah, I'll write about that. So what we'll have here is that now the so we have exactly the same number of inputs and outputs again. So of course, one question now should be, why did we do all the things? So what is different in this case? Is it now the same as if we have done like all the calculation the same? Or where was it different? Anybody has an idea? Yes?
The weights which we use for generation QV.
Yes. So there's weights in orange here, or like the second line there, they are different for the 2 parts. And so in the lower part, these values have differently influenced than in the upper case. And therefore, the resulting vector here, the blue, is not the same, because in the weighted sum, we have 2 different types of values in there. And that is therefore this opportunity that, for example, for the lower part, you might look at other parts than for the upper part. which you cannot easily do if you do just one single type of attention. And so that is what we're typically doing. So you're not changing the number of parameters. We're not now did the calculation independently. If you can even do the calculation mainly together, so there's no really big difference in how long it takes to compute it, to compute it. And then it's not even done only for two. So typically you might have something like 8 different heads or so, which all have the opportunity to look at different parts, which mainly means, yeah, you have different weights on the different parts, which are summed up. And you then can learn that like some dimensions are used to look at some aspects and other dimensions are there to learn at other aspects. Good. Yes.
You would need to have 2 different queries in this example, right? Or you would get the same result? Or...
I mean, you would, if you would have, I mean, you could have, of course, having somehow 2 different queries and doing that, but then you would have a lot more parameters or so. So the idea is here, you still have the one d-dimensional query, but you're just splitting the d-dimensional query into 2 and use that to calculate your weights. Yeah, so you're not having more really vectors. The only thing is, I mean, what you're doing with your weights, mainly you're saying the full vector, you're doing the scalar product. So you're comparing query and key, and you're saying I get one single number saying how important the query and keys are. In the multi-head, you're not getting one number, but you're getting how important is this position for the first part of the of your vector, and how important is it for your second part. And that's why you get 2 different importances there. Yes?
Isn't this architecture just weaker than the single-head attention? Would the single-head attention one also learn to do the calculation like this? Just split the vector into parts.
But it can only, I mean, in the single-head attention can only have one weight here at the end. So you always know the first position has an importance of 0.8 or so. Here you can say for the first one, it has an importance of 0.4, and for the second, it has an importance of 0.1. So you can like put different importance on that. And that is the main additional advantage you have. Good. Yeah, with this, we have done the main mass of self-attention. We'll on Thursday have a look at positional information, see how they are there or not there, and then have a look how to add that. And with that, thanks, and see you then on Thursday.